Welcome to today's Explainer. Today, we're tackling something that makes even seasoned Sparkies do a double take, sizing electrical conductors for an air conditioner. If you know electrical work, you know the standard rules of thumb. But for AC units, we literally throw some of those assumptions right out the window. We're going to see how sizing AC wire completely defies standard rules while staying 100% code compliant. So right off the bat, I gotta ask you, why on earth does wiring an AC unit break all the normal rules? I mean, an AC circuit looks totally different from your standard lighting or receptacle circuits. If you tried wiring a regular wall outlet the same way you wire a compressor, you'd fail inspection instantly, no question. So why the double standard? What makes that big metal box sitting outside your house so uniquely demanding? Okay, let's dive into this. Here's our roadmap for today. First, we'll look at why ACs break the rules. Second, we'll check out the nameplate cheat sheet. Third, we'll explain the 60-degree rule. And finally, we'll wrap it up with a real-world wire sizing example. All right, part one, why ACs break the rules. Before we calculate a single amp or strip a piece of copper, we really have to understand the why behind all these regulations. ACs are governed by completely different national electrical code rules, and it all boils down to one thing: the hermetic motor. Now, the compressor inside an AC doesn't use just any standard motor. It uses a hermetic motor, meaning it's completely sealed inside the compressor. And here's the real kicker. Instead of being cooled by the open air around it, it's actually cooled by the refrigerant itself. This highly specific setup is exactly why we can't just treat AC equipment like a standard electrical load. Because of that hermetic motor, AC equipment leaves the general rules in the dust and follows NEC Article 440. This article is packed with highly specific rules for conductor sizing and overcurrent protection, tailor-made for refrigeration equipment. If you take away anything from this, it's this: treating an AC unit like a regular light switch is a guaranteed recipe for a failed inspection. You can't just pick the smallest wire that clears the load on paper, you have to follow Article 440. Moving right along to part two, the nameplate cheat sheets. Now, since we're operating under a totally special set of rules, you might be thinking the math is going to be an absolute nightmare. But actually, the industry hands us a master key: the equipment nameplate. Every listed AC unit has to have one. You just need to find two vital numbers provided by the manufacturer: the minimum circuit ampacity, or MCA, and the maximum circuit breaker or fuse size, which is sometimes called the MOCP. These two numbers are literally the only starting points you need. They already account for motor characteristics, those crazy high starting currents, and all the internal loads. Now, if you know the NEC, you know it requires branch circuits for AC equipment to be sized at 125% of the rated load. When you hear that, it sounds like you're about to be doing some serious, intimidating math to figure out your wire size. You're probably dreading busting out a calculator on a hot job site to do fractional math, right? Well, here's the massive relief. Your job is not to recalculate. Your job is just to verify. With modern AC equipment, the manufacturer has actually done the heavy lifting for you. They've already run that 125% calculation. And the result? That's exactly what's printed as the minimum circuit ampacity, the MCA, right there on the nameplate. So when you read that MCA value, you can rest easy. The 125% rule is already baked right in. Okay, part three, the 60-degree rule explained. Now, what's really interesting about this next part is a common trap that catches so many folks. Here's the trap that trips up a ton of electricians, rookies and veterans alike. We've got our MCA from the nameplate, right? But picking the wire out of the NEC book isn't quite as simple as looking at a single column. Here's why. Even if you're holding premium 90 degrees Celsius rated wire like THHN or THWN2, your conductor ampacity is ultimately limited by the lowest temperature rating of the terminations in the circuit. You know, you're only as strong as your weakest link. So you're very often forced to limit your calculations as if that wire is only rated for 60 degrees. So why exactly do we do this? Well, for small HVAC branch circuits, our connection points are often physically limited to 60 degrees. We're talking about the disconnect plugs, the equipment terminals themselves, or even specific limitations of the cable type. Like if you're running NM cable, Romex. Because of these physical connection points, the safest, most code-compliant move is to size your conductors using the 60-degree ampacity column from the NEC table. It lines up perfectly with real-world inspection practices and completely keeps us away from dangerous, overheating assumptions. This quote from our source material really hits the nail on the head. You'll frequently see 90-degree rated conductors sized using 60-degree ampacity values in real-world installations. I really want to emphasize this because, man, it feels so counterintuitive to buy this high-performance wire and essentially downgrade it on paper. But I promise you, this practice is absolutely normal. It's expected by inspectors, and it's 100% code compliant. When in doubt, that 60-degree column is going to give you the most conservative and defensible result. All right, let's bring it all home in part 4, a real-world wire sizing example. Let's put all these clues together and solve an actual sizing problem, exactly like one you'd see out in the field. We know we're using Article 440, we know to check the nameplate, and we know to use the 60-degree column. So here's the data straight off our theoretical AC unit. The minimum circuit ampacity, the MCA, is 17.8 amps, and the maximum circuit breaker size is 30 amps. Remember, the manufacturer already crunched that 125% math to give us that 17.8 amp figure. That is our absolute baseline. Next, we take that 17.8 amp MCA and head straight over to NEC Table 310.6, specifically the 60-degree copper column. Looking there, a number 14 copper wire is rated for 15 amps. Well, since our MCA requires 17.8 amps, that 15 amp capacity of the number 14 wire just isn't going to cut it. It's too small. That pushes us up to the next standard size, which is number 12 copper wire. That gives us 20 amps, safely exceeding our 17.8 requirement. So the crucial point is how these two steps actually come together. Step 1, select the conductor. We know we need number 12 copper wire to handle the 17.8 amps. Step 2, verify the circuit breaker. The nameplate explicitly allows a maximum circuit breaker of 30 amps, so we're going to pair our number 12 wire with a 30 amp breaker. And here is the absolute climax of this whole explainer. Under the special rules of NEC Article 440, running a number 12 wire on a 30 amp breaker is perfectly 100% code compliant. No joke. If you did this on a standard lighting circuit in your living room, huge code violation because number 12 wire is normally capped at a 20 amp breaker. But because the conductor meets the minimum circuit ampacity and the breaker doesn't exceed the nameplate maximum for this specific hermetic motor, this installation is exactly right for an AC unit. At the end of the day, sizing wire for an AC unit isn't about memorizing complex engineering formulas. It's about knowing exactly where to look. It's about understanding that Article 440 applies, recognizing those termination temperature limits, and most importantly, trusting and following the manufacturer's nameplate. You definitely don't have to be a math genius. You just need to know how to read the cheat sheet printed right there on the side of the box. So I'll leave you with this final thought. The next time you walk past an AC disconnect and spot a 30 amp breaker sitting on a number 12 wire, a sight that maybe used to make you cringe or think someone's seriously messed up, will you now know exactly why it's perfectly safe and totally to code? I really hope this explainer has empowered you to look at HVAC wiring with a whole new level of confidence. Keep learning, keep verifying, and I'll catch you on the next explainer.